Hi students, today I am going to explain analysis of LR circuit. L means self-inductance of a inductor. R means resistor. That means I am considering a combination of resistor and inductor which are connected to AC source. Now I am going to do it. Till now we completed pure inductor, pure resistor and pure capacitor. Now I am taking the combination of resistor and inductor. When a resistor and inductor symbol is this. When a resistor and inductor, this resistance of this is R and the inductance is L, and I am connecting to a AC source. You know already inductor allows DC. When the direct current passes through a inductor means it's like a coil. So when the direct current passes through the coil, there is no change in the current, there is no EMF produced. So back EMF is not produced. So that's why you can say that the inductor allows DC, but when the AC passes through the inductor, what happens? Because of the change in the current, the back EMF is produced, which opposes the EMF which is given by us. Okay. So anyway, you know about the resistor. Let us go for discussion. Assume that this is the inductor of self-inductance cells L, and this is the resistance of resistance R. When the alternating current passes through this resistor, you know already, assume that this end is positive, this end is negative. After some time, this end becomes negative, this end becomes positive. So that means the current go on changes one direction to another direction. This is called the alternating current. Now when the alternating current passes through this circuit, you know, at a particular instant of time, you know already alternating EMF, the instantaneous EMF is nothing but E is equal to E0 sin omega t. At a particular instant of time, the instantaneous EMF is equal to E0 sin omega t. This is the cause of the circuit. This is the cause. Current is the effect. Now I am going to discuss where you know already when the two resistors are connected in the circuit, assume that this is R1 and R2. What happens? Then the voltage across the first resistor, voltage across the second resistor is sum of the voltages. Electromotive force is equal to V1 plus V2. But here these are not two resistors. One is resistor and one is inductor. You know already when I was discussing about the pure resistance, AC through pure resistance, I said the current in the resistor and the voltage across the resistor both are in the same direction. When I was discussing about the pure AC through inductor, I said the current in the resistor is I, but the voltage across the resistor is R. I said the current is behind the voltage by 90 degrees. So when I was explaining only inductor, I got I is equal to I0 sin omega t minus pi by 2. I think you can remember this. That means what? When the AC passes through inductor, at any particular instant of time, if the electromotive force is equal to E0 sin omega t, the current instantaneous current is I0 sin omega t pi by 2. That means the current is behind the voltage by 90 degrees. The current is behind the voltage. This is the voltage across the inductor. Voltage across the resistor is in the same direction of the current. But voltage across the inductor is 90 degrees behind the voltage. That means anyway there is no doubt this current and this current both are in the same direction. Because when the AC source is connected to resistor and inductor, the current passes through this resistor and this inductor. The direction of the current is same in both. If this is the current direction, here also direction of the current is same. But voltage across the resistor is in this direction, but voltage across the inductor is in this direction, which we already discussed. Now I am going to explain what is the combined effect of these two. Okay, let us go for that. You know, if the two resistors are connected, one is resistor R1 and one is resistor R2, then the voltage, for example, this is the EMF. EMF of the source is equal to instantaneous EMF is sum of the voltage is these two voltages, because this is resistor, this is resistor. So voltage across this resistor, voltage across this resistor, both are in the same direction. That's why you can add normally. But here the voltage across the resistor, voltage across the inductor are not. They are perpendicular to each other. This voltage across the resistor, current, this current, both are in the same direction. But voltage across the inductor is perpendicular to this. But in this case, how can you do it? Very simple. If you see this, if you see the combined effect of this, the electromotive force at any instant of time, the electromotive force in the circuit is equal to VR square. You know, electromotive force or potential difference, both are same, or voltage. Voltage across the resistor plus voltage across the inductor. You cannot write like this, because here VR and VL both are not in the same direction. So you cannot add directly. Even though electromotive force is scalar, you cannot add directly. But as this VR and VL, see here, finally you can write like this. VR and VL both are perpendicular to each other, because the VL is perpendicular to current here, but VR is parallel to the current. That's why you can write VL is perpendicular to VR. When this VL and VR, voltage across the resistor, voltage across the inductor, this combination, the net EMF becomes VL square plus VR square under root. It is like this, similar to the Pythagoras theorem. That means the net EMF is, the net voltage across this combination is sum of these voltages. But which sum? It is similar to the vector sum, but even the voltage is not a vector. So the VL is in this direction, VR in this direction. That's why the net electromotive force of this combination is making certain angle with this. Assume that this is phi. So you know, E is equal to under root VL square plus VR square, or you can write VR square plus VL square. Both are same. You can write this as, VR can be written as, just see, VR can be written as, V means what? IR whole square. According to Ohm's law, voltage across the resistor is conductor and this, plus VL can be written as current and resistance of this, you know, resistance of the inductor is considered as XL. This is called inductive reactance. Inductive reactance. Here resistor of the resistor opposes the current. That's why I into R. It is denoted by R. But here inductor also opposes the current. That opposition offered by the inductor to the current is called inductive reactance. It is also similar to resistance. So that's why you can write it as current into resistance. Current into resistance of the inductor is XL. So this is also having square. So you can write it as IR square. I square R square. So I square is common. Then R square plus and XL square under root. Then I is coming outside. Then you can write it as R square plus XL square. You know, XL is nothing but omega L. We already discussed when I was explaining AC through pure inductor. I said the inductive reactance is nothing but angular frequency and inductance of the inductor. So this can be written as omega L, omega square L square, because in the place of XL I am writing like this. So here This is nothing but electromotive force. Electromotive force in the circuit at any instant of time, the instantaneous voltage or instantaneous EMF at any instant of time is current, instantaneous current into this. But what is this? This is nothing but, you know already, electromotive force. This can be written as I into this square root of r square omega square can be written as ZL. Here that means this part is considered as ZL. That means I already said R is the resistance offered by the resistor. Omega square L or XL, this is the resistance offered by the inductor to the current. But the combined resistance of these two, resistor and inductor, both are acting as a single component and they are offering certain resistance to the current. The resistance is called inductive impedance. This is called what? Inductive impedance. Inductive impedance is also a resistor. It is also measured in ohms. There is no doubt. So, resistance is measured in ohms. Inductive reactance is measured in ohms. And inductive impedance. You remember, inductive reactance means we are talking about only inductor. Resistance means only resistor. But the combined opposition offered by the inductor and resistance is called inductive impedance. It is also measured in ohms. So that's why you can write E is equal to IZL. Here, you know, according to Ohm's law, V is equal to IR. Here V means E, I means I, but in the place of R, I am taking the effective impedance. What is this? This under root R square plus XL square. XL square is called inductive reactance. This is resistance of the resistor. Both are opposition offered by the resistor and opposition offered by the inductor. But this combination is called what? ZL. Here ZL is nothing but under root R square plus XL square. Here XL is nothing but omega square L square. This is called inductive impedance. ZL is what? ZL is nothing but inductive impedance. So it is also measured in ohms. Now how can you explain in the phasor diagram? In this LR circuit, I said this is x-axis and this is y-axis. If you consider VL is in this direction, VR is in this direction, there is no doubt the current is also in this direction, because I said resistance of the current. Because I said the current in the resistor and voltage across the resistor both are in the same direction. That's why the voltage across the resistor and current both are taken along the x-axis. Then voltage across the inductor is taken along the y-axis. But the resultant of these two is taken as E. This net electromotive force offered by the resistors and inductor. You remember, this is what actually, this is the VR, but this is VL. VL may be in this direction, but I am saying this is the resistance voltage across the resistor. This is the voltage across the inductor. This voltage across the resistor and voltage across the inductor are showing along the x-axis and y-axis. The net EMF across these two is like this. By using the Pythagoras theorem, you can write this net EMF at any instant is making certain angle phi. So this is about the phasor diagram. That means the phasor which is showing the instantaneous EMF at any time is making an angle phi. This is called phase angle with x-axis. But in case of, I said when I was explaining about the pure resistor, voltage across the resistor and current in the resistor both are in the same direction. That's why voltage, the phase angle is how much here? 0. Because there is only one voltage which is across the resistor when I was explaining pure resistor, AC through pure resistor. But when I was explaining pure inductor, current is in this direction, voltage is in this direction. There is only one voltage, that is VL, which is making 90-degree phase angle. Here phase angle is how much? 90 degrees. When it is only resistor, phase angle is 0. Phase angle means the instantaneous, at any particular instant of time, the net EMF, net voltage and current are inclined. Net voltage and current are making certain angle with each other. That is called phase angle. But in case of pure resistor, phase angle is 0. But in case of pure inductor, phase angle is what? 90 degrees. That means in pure inductor circuit, voltage and current are 90 degrees out of phase. But in case of this, the net EMF of VR is resistance, VR is voltage across the resistor, VL is the voltage across the inductor. The combined effect, the combined EMF, instantaneous EMF at any instant of time is making the angle which is less than 90 degrees. But definitely it is more than 0 degrees. So the phase angle is more than 0 degrees, less than 90 degrees. It is an acute angle. Clear? So this is about phase. This is called phasor. If you want to find out the phi value, how can you find out? Very simple. If you know the voltage and this, you can find it. So this is voltage across the inductor. This is voltage across the resistor. Then tan phi is equal to VL by VR. Opposite side by adjacent side. It can be written as IXL by IR. Voltage is nothing but current into resistor, but the resistance of the inductor is considered as inductive reactance. This is I into R. II gets cancelled because same current passes through resistor and inductor. So that's why the tan phi can be written as tan phi is equal to XL by R. Here XL is what? Omega L. Angular frequency and self-inductance divided by R. If you know these values or these values, you can find the phase angle. So finally, I can say that here the net current is out of phase with phi angle. That means here current in the resistance and inductive circuit, the current is not coinciding with the electromotive force, but it is making certain angle called phi. That means current is behind the electromotive force with angle phi. Phi value may be any angle between 0 and 90 degrees. This is about LR circuit. I hope you understood.